Now, in the previous recording, we discussed how a derivative of a function is also a function. Since the derivative of a function is also a function, we can draw its graph. Consider the function at the top. If we want to sketch a graph of its derivative, we need to remember that the derivative is the slope of the graph, of the tangent line of the graph at each point. And so, for example, if we look at point A, which has a slope of 0, since the derivative of A, or the derivative at A is its slope, then the derivative at A will have a value of 0. The other place where the derivative is 0 is here at D. That means at D, our derivative function will also be 0. Notice that between A and D, we will all have tangent lines with negative slopes. That means that all the values in between A and D will take on negative values. Notice some specific points like B has a slope of -1. That means at B, our y value for our derivative is -1. At C, we have a slope of -4/3. So at C, our derivative has a value of -4/3. Notice when we go to the right of D that all these points will have positive slopes. That means that the derivative there is going to be positive. At point E, we have a slope of 2. So at our derivative function, at E, our y value will be 2. Now, if we want to consider the derivative at an endpoint, we need to remember those will be one-sided limits. If we want the derivative at a leftmost endpoint, then we will have to take the derivative as h approaches that endpoint from the right. If we want to find as h approaches 0 from the right, if we want to find a derivative on the right endpoint, we'll need to take the limit as h approaches 0 from the left. Now let's consider the absolute value function. If we look to the right of the origin and we think about the slope of this line, well, to the left of 0, the absolute value of x is going to be -x, which we know has a slope of -1. So the derivative of the absolute value of x to the left of the origin is -1. To the right of the origin, we're going to have the line y equals +x, which we know has a slope of 1. So to the right, the derivative is 1. This function is not differentiable at the origin at 0 because the derivative from the left and from the right, the left-hand limit, or the left-hand derivative and the right-hand derivative are not equal. So this function is not differentiable at 0. We can look at this and see that it has a corner at 0, and any graph that has a corner will not be differentiable at that corner. Now here are some examples of when a function does not have a derivative at a point. And again, number 1 is where we have a corner, and you can see how this comes up into a point. The one-sided derivatives will be different. Where there is a cusp, where the slope of PQ approaches infinity from one side and negative infinity from the other. And so these are getting steeper and steeper and steeper. Where we have a vertical tangent, and you see here this pink line is a vertical tangent. So at P, there is no derivative. And anywhere where it's discontinuous, there will not be a derivative there. Now, differentiability implies continuity. If f has a derivative at x equals c, then f is going to be continuous at x equals c. So if it has a derivative at that point, it will be continuous at that point. Now, another theorem that we want to look at here, if a and b are any two points in an interval on which f is differentiable, then f prime takes on every value between f prime of a and f prime of b. You'll notice that that looks very similar to the intermediate value theorem that we discussed earlier. If our function is differentiable between a and b, then it is continuous between a and b. And so its derivative must take on every value between f prime of a and f prime of b. Now this is the unit step function we've seen earlier. It does not have the intermediate value property, and it cannot be the derivative of a function on a real line.